NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will master a reliable algorithm for solving equations of the form log base a of f of x equals log base a of g of x. We'll visualize each rule and then apply it to a concrete example. Step 1. State the equation and remember the base conditions. The base a must be positive and not equal to 1. Step 2. Convert the equation into an equivalent system using the argument of the left logarithm. We require f of x to be greater than 0, and we set f of x equal to g of x. Step 3. Alternatively, use the argument of the right logarithm. Require g of x greater than 0, and again set f of x equal to g of x. The two systems are equivalent. Choose whichever inequality is simpler to analyze. Example. Problem 1 reads, log base 10 of open parenthesis 4 minus x close parenthesis equals log base 10 of open parenthesis 6 minus x close parenthesis minus log base 10 of x. Step 1. Apply the quotient rule of logarithms. A difference of logs equals a single log of a quotient. Step 2. Use the 1-to-1 property. If log base 10 of a equals log base 10 of b, then a equals b. Step 3. Clear the denominator by multiplying both sides by x. The right side becomes 6 minus x. In the source text, this line was briefly written as 6x, but the correct step is 6 minus x. We proceed with the corrected equality. Step 4. Distribute x on the left and keep the right side as 6 minus x. Step 5. Move all terms to one side to make a quadratic equals 0, matching the exact structure of the provided solution. Step 6. Combine like terms, negative 4x minus x equals negative 5x. Step 7. Factor the trinomial. We need two numbers that multiply to 6 and add to negative 5, negative 2, and negative 3. Step 8. Apply the zero product property to get x equals 2 or x equals 3. Step 9. Check the domain of the logarithms. Each argument must be positive. We require x greater than 0 for minus x greater than 0 and 6 minus x greater than 0. That means 0 is less than x, which is less than 4. Both solutions 2 and 3 satisfy the domain. Example. Problem 2 reads, log base 3 of 5 plus log base 3 of x equals log base 3 of 10. Step 1. Apply the product rule of logarithms. A sum of logs equals a single log of a product. Step 2. Simplify the product 5 times x to get 5x. Step 3. Use the 1-to-1 property to equate the arguments. Step 4. Divide both sides by 5 to get x equals 2. Since x must be positive for the logarithm, x equals 2 is valid. Summary. For problem 1 we found x equals 2 or x equals 3, both valid in the domain 0 to 4. For problem 2, we found x equals 2. The main ideas were the product rule, the quotient rule, the 1-to-1 property, and careful algebra with domain checks. Example. Problem 1. Log base 4 of a plus log base 4 of 9 equals log base 4 of 27. Step 1. Use the addition property of logarithms. Log base b of x plus log base b of y equals log base b of x times y. Step 2. Apply the 1-to-1 property of logarithms. If log base b of x equals log base b of y, then x equals y. Step 3. Solve for by dividing both sides by 9. So it equals 3. Now we move to problem 2. Problem 2. Log base 10 of 16 minus log base 10 of 2x equals log base 10 of 2. Step 1. Use the subtraction property of logarithms. The difference becomes a single log of a quotient. Step 2. By the 1-to-1 property, set the arguments equal. 16 over 2x equals 2. Step 3. Multiply both sides by 2x to clear the denominator. That gives 16 equals 4x. Finally divide both sides by 4. Therefore x equals 4. Summary. For both problems, we combined logarithms, used the 1-to-1 property to equate arguments, and then solved the resulting simple equations. Our answers are at equals 3 and x equals 4. Let's begin. Problem 1. We start from the equation. Log base 7 of 24 minus log base 7 of x plus 5 equals log base 7 of 8. Step 1. apply the quotient rule of logarithms to combine the left-hand side. Then write the combined form exactly as in the image. Step 2. Since the bases are equal, equate the arguments. Step 3. Multiply both sides by x plus 5 and expand the right side. Step 4. Move 24 to the right to match the exact intermediate form. Step 5. Isolate the x term. Step 6. Divide by 8 to finish. Problem 2. Start from the given equation. Log base 2 of n equals 1/4 times log base 2 of 16 plus log base 2 of 49. Step 1. Use the power rule to move 1/4 into the exponent on 16. Step 2. Replace 16 with 2 to the 4th power, exactly as shown. Step 3. Simplify the exponent product 4 times 1/4 to get 1, leaving log base 2 of 2. Step 4. Use the product rule to combine the two logs. Step 5. Multiply 2 and 49 to obtain 98. Step 6. Equate arguments to solve for n. Final results. For problem 1, x equals -2. For problem 2, n equals 98. Example. Solve the equation. Log base of 4n minus 2 log base of x equals log base of x. First, apply the power rule to 2 log base of x. Next, apply the quotient rule to combine the logs. Since logs with the same base are equal, equate the arguments. Multiply both sides by x squared. Finally, take the cube root of both sides to solve for x. Second equation. Apply the power rule to both sides. Next, use the product rule on the left-hand side. Equate arguments of the logarithms. Recognize that 8n cubed equals the cube of 2n. Take cube roots. Finally, solve for x. Summary. We followed the exact algorithm without reordering steps. First solution, x equals the cube root of 4n. Second solution, x equals 2n plus 1. Practice by applying the same sequence of rules on new plus 1. Practice by applying the same sequence of rules on new equations. Example. Problem 1. Solve the equation. Log base 10 of z plus log base 10 of z plus 3 equals 1. Step 1. Use the product rule. The sum of logs with the same base equals the log of the product. Step 2. Multiply the factors inside. Z times z plus 3 equals z squared plus 3z. Step 3. Convert to exponential form. If log base 10 of equals 1, then a equals 10 to the first power. Step 4. Move all terms to one side to form a quadratic. Step 5. Factor the quadratic. Z squared plus 3z minus 10 factors as parenthesis z plus 5 times parenthesis z minus 2. Step 6. Apply the zero product property to get two candidates. Step 7. Check the domain of the original logarithms. We need z greater than 0 and z plus 3 greater than 0, which together require z greater than 0. Therefore, z equals -5 is invalid, and z equals 2 is valid. Problem 2. Solve the equation. Log base 6 of a squared plus 2 plus log base 6 of 2 equals 2. Step 1. Combine the logarithms using the product rule. Step 2. Distribute the 2 to get 2 a squared plus 4. Step 3. Convert to exponential form. Step 4. 6 squared equals 36. Step 5. Subtract 4 on both sides to isolate the a squared term. Step 6. Divide by 2 to get a squared equals 16. Step 7. Take square roots at equals plus or minus 4. Check the domain. The argument a squared plus 2 is always positive, so both values are acceptable. Summary. Use the product rule to combine logarithms, convert to exponential form, solve the resulting algebraic equation, and always check the domain of the original logarithms. Final results. Z equals 2 for problem 1, and for problem 2, I equals plus or minus 4. Step 1. For logarithms, equal logs with the same base imply equal positive arguments. That gives an equivalent system, argument positivity and argument equality. We require 2 over x plus 1 to be positive, which means x plus 1 is greater than 0, and we set the two arguments equal. Step 2. We now focus only on the equality of arguments. Step 3. Cross multiply 10 with 2 and multiply x plus 1 with 2 plus x. This yields 20 equals the product x plus 1 times 2 plus x. Step 4. Expand the product using distribution. We obtain 20 equals x squared plus 3x plus 2. Step 5. Subtract 20 from both sides to write a standard quadratic. Step 6. Factor the trinomial x squared plus 3x minus 18 factors as left parenthesis x plus 6 right parenthesis plus 6 right parenthesis times left parenthesis x minus 3 right parenthesis equals 0. Step 7. Apply the zero product property. We get x equals negative 6 or x equals 3. Step 8. Check the domain condition x greater than negative 1. Negative 6 violates the domain, so it is rejected. 3 satisfies the domain. Therefore, the solution set is left brace 3 right brace. Final answer x equals 3. The valid solution set is curly brace 3. Example. Solve the following equations. Step 1. Remove the logarithms using the equality property. If log base b of m equals log base b of n, then m equals n. Step 2. Rearrange to standard quadratic form. Step 3. Factor the quadratic. We need two numbers that multiply to negative 15 and add to negative 2. Step 4. Apply the zero product property to get the candidates. Step 5. Check the domain. The argument of a logarithm must be positive. 4x equals negative 3. 2x is negative 6, which is invalid. Therefore, x equals negative 3 is rejected, and x equals 5 is valid. Now, the second equation. Step 1. Remove the logarithms by equality. Step 2. Rearrange to standard form. Step 3. Factor the quadratic. We need two numbers that multiply to negative 30 and add to rearrange to standard form. Step 3. Factor the quadratic. We need two numbers that multiply to negative 30 and add to negative 1. Step 4. Apply the zero product property to solve. Step 5. Check the domain. For logarithms, arguments must be positive. X equals negative 5 is invalid because log base 10 of x would be undefined. X equals 6 is valid. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.